So from there, what happened? Well, my dad is he was the CEO. He just passed away a couple of months ago. He was the CEO of a construction company, and my mom was an IT director at AT&T at the time. So my dad had built things like the main gate at Disney and the air traffic control tower at the airport. And my mom, led the Y2K IT revolution for AT&T and Lucent and et cetera, et cetera. So neither one of them knew anything about chemistry or forensic science. Matter of fact, my mom didn't even think it was a real career. She was like, nobody can solve crimes using science. And I was like, but they can. And at the age of 13, I dedicated my future career to pursuing that. So I started this by getting a degree in chemistry at Howard University. But I don't know if it's just a thing about Howard, because it's not a thing at UCF. Every summer, it was expected that you had an internship. And it was hard to get into internships at forensics. So I did an internship at orthobiotech, doing some cancer research. I ended up doing 3 years at Colgate-Palmolive through the Inroads program. And I was doing hand dish soap research, laundry soap research. And then I was able to get in a co-op or an internship during my last semester at Howard University with the ATF, where I was doing explosives research. I also did an internship at the National Center for Forensic Science, which is where I work now, just by calling them out of the blue and saying, hey, I want to come and do research with you. Because at that point, I had already called the FBI and said, what is it that I need to have in order to work for you? And they ran me through several people. And then finally I spoke with somebody who explained, this is what you need to have. This is what you can do to better your resume. After that, I came to UCF to get a PhD in chemistry with a focus in forensic analysis. And I was one of the first people in the country to have that degree. But while doing my dissertation, I worked every summer at the South Carolina Law Enforcement Division developing analytical methods for glass and paint. And these were methods that they were also interested in implementing. So I kind of validated it for them. And then I moved, after graduating UCF, after getting my postdoc, and after teaching at Howard University, I went and started working at the US Army Criminal Investigation Laboratory, where you see Detective Mickey. And it's now called the DFSC. And from there, I moved to UCF. So I got a PhD. I already went over this, but basically I did research. I did research as an adult, pseudo-adult in grad school. And I did research at Howard University, where I was using MALDI time-of-flight mass spectrometry to identify the concentrations of folic acid with an intent of monitoring people who had low levels of folic acid, and it could lead to biological issues. So none of it actually had anything to do with forensic science as I was an undergrad, but I tell students all the time, to be a good forensic scientist, you have to be a good scientist. And to be a good scientist, you have to know various aspects of your craft, i.e. me, chemistry. I did all types of chemistry just so I could get to the point where I was a good forensic scientist. So where am I today? For those of you who came in earlier and saw those silly faces that I was making, I forgot my camera was still on. I was trying to Google a picture of myself and I found this image of me on Tumblr. Shocked the shit out of me. But I am an associate professor at UCF. I have a joint appointment with the Department of Chemistry and the National Center for Forensic Science. I am also CEO and lead consultant of my own company called Forensic Science Research and Consulting, where on the side I help attorneys kind of decipher the mystery that is chemistry. A couple of thoughts that I love to share about my journey is if you're in school or looking to pursue a grad degree or a post-grad degree or something like that, the school is a good choice, but it's really all about the science. So if you have a good scientific mentor, you'll be a great scientist, right? Internships are so important, internships and experience. One of the things that I learned was when you're trying to identify your career, it's good to have experiences that, hey, reinforce, yeah, this is something I want to do. But it's also really important to have experiences that say, yeah, no, this is not what I want to do with the rest of my life. And experience is always the best teachers, right? You learn both from good experiences and experience where you're like, oh my gosh, I promise if you get me out of this, I'll never do it again. And usually you don't. So what is forensic science? And I love to have this kind of conversation because a lot of people have this perception that forensic science is whatever they see on TV, such as these wonderful TV shows, which I'm sure you've seen once or twice, or at least a commercial of it. But this is what we really look like. Rarely do we leave the lab unless you are in a designated discipline that is required to go to the scene, such as crime scene. In my lab, the only people that were really designated were the digital evidence, and because they may have to go out and take a 3D scan of the crime scene. There were a couple of times where I myself could have gone to a crime scene. Say it was a really big crime scene, and the crime scene people, they were like, look, we need help bagging all of this so we do it properly. They might ask us to come out, but generally we never leave the lab, and we never talk to suspects or witnesses unless the suspect is acting as his own attorney. Then there's nothing else you can do. The definition of forensic science is a little broader than most people assume. They usually think it has something to do with DNA, but really it's the application of any science or technological field to a civil and or criminal investigation. You have two types of forensic scientists: those that work in the lab and their job is to collect, preserve, and analyze evidence and present it in a court of law. And then you have the forensic science researchers who are tasked with helping develop new analytical methods that actual operative crime labs can implement. Because when you're working in a crime lab, depending on if it's a federal, state, local, depending on if you're in Miami or Oklahoma, you may have thousands of crimes a year. You don't have time to develop new methods that help advance the science. And so forensic researchers are there to do that. There are several types of crime labs. Most people automatically think of, say, the FBI or their local crime lab. In Florida, it's FDLE, Georgia, it's GBI, New Jersey, it's NJI. Oops, don't tell them I forgot. But at the federal level, in addition to the FBI, there is ATF, Homeland Security, Secret Service has their own crime lab, the DEA, of course, and the Postal Service has their own. And most people are like, why? And that's because anything that goes through the post office is under the jurisdiction of the Postal Service. So mailing bombs, mailing death threats, mailing ricin. So they have to be able to analyze it and then go out and arrest the suspect. The one that makes me laugh all the time is somebody had videotaped himself threatening Governor Whitman in New Jersey and put his return address on it. So the Postal Service doing the investigation was able to go directly to his house and arrest him. And the military side of the house, while it's federal, it still stands as its own. So it has the now Defense Forensic Science Center, which does traditional forensics. You have the Joint Prisoners of War Missing in Action Accounting Command. They do forensic anthropology to identify war remains and return them to their families. You have the Digital Cyber Crime Center, that's all digital evidence, and then the Armed Forces Medical Examiner System that does does autopsies and death investigations on recently deceased personnel. So while both this agency and this agency both deal in identifying dead servicemen and women, these people do it for things like, the Korean War, something like that, where this might be somebody who just passed away and was shipped home. At a state level, every state has their own system of crime labs. Counties will have their own, and large cities will have their own crime lab. And usually these three, like in the state of Florida, FDLE, the counties, and the Orlando Police, they all kind of work together, where these smaller agencies will default to FDLE. The one that you may not have heard about are private crime labs. So Walmart, Target, and even Quest Diagnostic do offer their own forensic investigations that are helpful for their own people. More so Walmart and Target. Quest, they will do forensic toxicology analyses. So they're not doing the investigation, they're providing a service for an investigation. Whereas Target will actually analyze their own latent prints, analyze their own digital evidence in order to find thieves mostly. Now, there are several areas of forensic science. You have the traditional ones. These are people that do it. This is their job 24/7. Every day they go in, they analyze crime scenes, they analyze evidence, et cetera, et cetera. But then on the right side, you have consultants. And these are people that operate as a psychologist primarily. That's their job. But when the police have a need for you to kind of analyze or talk to a potential suspect, they'll bring in one of these consultants, and now that person is operating as a forensic psychologist or an odontologist. So they're a dentist all day, but then the police need you to identify a human remain using teeth. Now you are a forensic odontologist in that moment. So just to highlight a few, there are firearms examiners, there are document examiners. They'll look for like forgeries or fraudulent documents, shredder cases like the Enron. You have latent prints examiners that try to identify a latent mark on evidence and compare it or identify it based on a known print. You have a psychologist. You'll see they're criminal profilers, or they try to understand the mental state of a potential suspect or victim if necessary. Odontologists, engineers. So if a bridge collapsed, they try to find out if it was nature that caused it or was it due to poor construction. Anthropologists identify remains. Artists are still very important to bring to life the face of the victim and or suspect. And then for those people who have an interest in bugs, which I don't, there are entomologists, and they are usually really helpful in identifying how long a body has been deceased based on the animals that have come to either hibernate in the body, feast on the body, or lay their eggs in the body. And we do all of this because there's a variety of new weapons that show up every day. Most recently, while smartwatches and what are they called? Alexas? Well, yeah, these things. I don't have one. But these are not necessarily weapons, but they have become a really good source of information about the potential victim or suspect, right? So if you were wearing a smartwatch, they could narrow down your time of death by determining when your heart stopped being monitored, right? There was a case where somebody was murdered in their house, and that person happened to have an Amazon device, and they wanted Amazon to give them access to the recordings, because Amazon, or what is it, Alexa, is always listening for you to say, Alexa, right? So if it's always listening, then it was likely listening at the time this victim was saying, Bob, stop killing me, or why are you doing this, or whatever. So they have a lead. So anything can be used in a forensic investigation if it provides information about that case. So if you're ever interested, there are different qualifications to be a different there are different qualifications for different disciplines in forensic science. They do not all require the same type of training because they all require different skill sets. So to be a traditional scientist, so these are your chemists, biologists, latent print people, getting a BS, having some research, some math is always a great experience. To do digital evidence, you need a degree in computer science, electrical engineering, physics, math, or even information technology. Crime scene, you could get a degree in criminal justice or forensic science. Sometimes they'll even accept an associate's degree or a high school degree, because most of these fields, they just need you to come in with the basics and they will train you to do what they need you to do. And if you ever pursue a forensic science degree, it doesn't give you preference to work in a lab. They always look at the courses that were offered. Like, do you have 30 hours of chemistry? Now, if you're interested in something like forensic psychology, forensic anthropology, any of those consultants, then you need a degree in anthropology, psychology, sociology, dentistry, because that is the basics for your application to the science. Okay, so what do? I try to develop methods that help increase the number of tools used in sexual assault investigations, because they are unfortunately still rampant in America. The most recent report that I found, I think I actually found in 2018, I just haven't updated this slide, but approximately 1.4 people out of 1,000 have admitted or shared that they were raped or sexually assaulted, which is almost a 30% increase from just the year before, right? And that might be because more people are feeling supported when they share their stories. The other thing that has been noted is that there is an increased use of condoms occurring in sexual assault cases. And this is because more people are cognizant that DNA can be a unique identifier to somebody. So if I can remove, say, sperm or semen, assuming that the suspect is a male, then they limit the idea of them finding out that it was me. So this is also present in a study that was done in 2012, where almost 11,000 sexual assault kits were not submitted in LA County. And so they decided, well, what if we looked at that? How could it have changed or affected the investigation? So they pulled out about 2,000 kits, and here's like the breakdown of how it goes. But the pieces that I want you to focus on is line number 1. Out of the 2,000 cases, nearly 33%, there was no DNA found. And in the cases like this, sometimes they'll just say, look, there's nothing we can do. And they dismiss the case because there's no evidence. And that's kind of where I want to say, no, if we don't have DNA, we may have lubricant residue that can provide a link between the suspect and the victim, which is really all forensic science does. We never know what the truth is, but if we can link the suspect to the victim, the suspect to the crime scene, or the crime scene to the victim, and increase the number of linkages between this crime scene triangle, it increases the likelihood that something bad happened, right? So that's one. Number 2, only 36% of the 2,000 cases yielded a full DNA profile that could go to CODIS. So now you're talking about, out of these 2,000 cases, you'll only be able to get identification out of 36% of them. 350 yielded a positive CODIS hit, which means they identified an offender. 90% were already convicted. 90 were already convicted. 147 were an identified offender. There were 70 unidentified offenders, and then 13 undetermined. They didn't have any real information, but they know that it matched something. And they also found 27 case-to-case hits. Now, what these are is that I don't know who the suspect is, but I have found the suspect's DNA in 4 cases. So whenever I find the suspect, I can charge them on these 4 cases, right? The other thing to note that was interesting in the study, they said that most kits were not submitted because the detective said there's no suspect. So why am I going to submit this if the victim says that, well, I don't know who it is? And instead of just submitting it and saying, hey, let's see if we find somebody, even if it becomes a case-to-case hit, at least we have that information. The other thing that was really interesting about the study is that they said there were no new arrests after the 371 kits yielded a positive CODIS response. They were able to file charges in one new case. 2 people were convicted on this case, but they were already in jail for another crime. And 40% of the cases the suspect was already arrested on this case without the benefit of DNA. And by quote, they say, in many cases, DNA testing of evidence is not necessary for there to be a plea or a conviction in a sexual assault case, because that's just good old gumshoe detective work. They're really good, or there's other evidence that provides that link. So if DNA is not as prevalent as we expect it to be, then what other tools can we use to assist in sexual assault investigation? Now, in a sexual assault kit, it's not really this idea that you might have in your head. It's basically a box containing envelopes that are used to collect different aspects from the victim and or suspect if they have one. So here's like a little graphic of what's in there. So there are swabs, and they'll like comb hairs, pubic hairs to get hairs from the suspect, and those will be packaged and sent to DNA. Blood collection, when they scrape underneath your fingernails, all of that will go into DNA, hoping to get some biological evidence of the suspect. But there's several aspects that will go to the chemistry side of the house. So clothing, underwear, those things will go looking for lubricant residues. Combings may go in for hair analysis, and cotton swabs, they will either be submitted for lubricant. If it's saliva they're collecting, they might also analyze that for drugs to see if it's a drug facilitated sexual assault. Because there are a host of other types of evidence that occurs. So it's not just DNA, but latent prints are a big aspect of sexual assault investigations. Drugs, obviously, if there are powders or pills in the area that were used to render the victim unconscious, that's important. Digital evidence has become like the one thing that we look for in every case, because what do you call those people? Suspects are stupid. A lot of them tend to put their crimes on social media. So if you see things on social media that look suspicious, that's a great place for detectives to start. Text messaging, GPS location. Every time you go to your friend's house, there is a ding on their Wi-Fi router saying, hey, this phone tried to connect to me. And that's something that digital evidence people can look back and say, yeah, your phone was in the vicinity of this crime at this time, right? So that's kind of why I started looking into the area of forensics lubricants, because when I came to UCF, I realized that while some labs have done it, there is a void of supporting research. And I'll get into that a little bit later, but why would you want to look for sexual assault lubricants? And one of the ones that I think about all the time came from a detective in Orlando. He said, when I shared my research with him, he said, well, when is this going to be available for us? And I was like, probably a couple of years. He goes, because, we've had cases where it's a minor that's being sexually assaulted by an adult. And we'll find several bottles of lubricants around the house. And we want to know which one might have been used on the child, because we all know that most serial criminals are ritualistic. So if it worked one time, they'll use it again. So if this suspect is assaulting a child, most likely they're going to use one bottle and they're going to hide it from everyone else. So if I can associate the lubricant found on the victim to one of the bottles in the house, then the fingerprints and or, low copy number DNA from skin cells can be used to identify who that assailant is. So I started out to say, okay, since lubricants are complex chemical mixtures, and I used to do ignitable liquids analysis and explosives for the military, this is basically the same thing. Can we develop a classification methodology that crime labs can use in the event they have an unknown? I don't know what it is. It doesn't even have a scent to it. What sort of lubricant is this that provides more information than just it has polydimethylsiloxane and glycerol, right? So I asked myself, is there a way that I can associate samples to a common source, right? Because PDMS is everywhere. It's on your food, it's on your clothes, it's on your underwear, it's everywhere, not just in lubricants. And can you classify lubricants in the absence of DNA? And are we able to have enough unique features about lubricants that I could develop a database that any crime lab can use? And that's where I started my research. So if you ever go to CVS or Amazon and look to purchase lubricants, you'll find thousands of versions of lubricants, but they usually fall into five marketing types. You have water, which usually will have either glycerol, polyethylene glycol, some parabens, and water. You'll have silicone-based, which is a version of polydimethylsiloxane, oils, organic/edible. So these will have like fruit essences, butters, aloe, and then you have condoms, which will usually have either water or silicone, but they also have octylamine and inoxidil 9, which is a spermicide that'll differentiate it from a bottled lubricant. And then there are subcategories that honestly, when I started this, I didn't even know if it would really be helpful, but we have demonstrated to be. You have anesthetics, which are things like lidocaine or benzocaine, sensations, which things are like make it really cool, really hot, and then flavored. And we found that maltol, ethyl maltol are used in flavored lubricants to hold the fruit oils in suspension with the water. And here are those components. In terms of PDMS, this is the one where there are like 17 different versions. It was really 7, but I over exaggerate, of PDMS. One that are trimethyl terminated, you have hydroxy terminated. There are ones that just have hydrogen on the ends. You have cyclics, you have various ones. Now, while GCMS is the gold standard in forensic science, it isn't all that helpful in lubricant analysis, because if you have a silicone-based lubricant and you don't know it's a silicone-based lubricant, most people do not want to run it through their GCMS because the column is silicone, and running siloxanes through a silicone-based column usually degrades the column faster. So the current technology of doing lubricant analysis is a 3-part process. You try to extract out cornstarch, which is a dry lubricant in condoms, and you can identify that under cross polars and PLM. You take the hexane fraction, hexane extract of your sample, and you run it under IR to identify the presence of PDMS. And then you take your methanol fraction and you run it under GCMS to identify flavors, fragrances, and inoxidil 9. But this is what some lubricants can look like, just a mass of unresolved material on a GCMS. This is from a case that happened at a military base in 1980 something. But if you're looking at this, in these sorts of cases, you have to be able to match almost every single component in order to say that an unknown sample matched one of these reference samples. So I started exploring a technique called direct analysis in real time of-flight mass spectrometry, which is an ambient ionization technique that is done through Penning ionization. It has high resolution because it's a time of flight, and we can measure nearly anything that has a massive charge somewhere between 40 and 2,000. The best thing about it is that I can do a full scan analysis in less than 5 seconds. And there's little to no sample prep. So I can analyze solids, liquids, or gases. And really all you have to do is stick your sample in between the mass spectrometer and the ion source, and it will ionize nearly everything that is on your sample. But you have to analyze positive and negative mode individually because there are some molecules that just do not take a hydrogen, they'd rather release a hydrogen, such as your hydroxides. You'll see them better in negative mode. You might see them in positive mode, but it's better to see negative mode. So we did a quick sample. We analyzed 90 samples 5 times on the DART, and we chose some anesthetics, sensations, different flavors, spermicidal. So we could see, are we able to uniquely identify it, or does the base of the lubricant take over and you don't see any minor differentiating features? This is what a DART spectrum looks like. Not inherently, I just did a head-to-head of positive ion mode and negative ion mode. But each peak, because we do soft ionization, each peak is an individual component. So on the positive side, you'll see glycerin and a dimer of glycerol. You'll see the maltol, which we find in flavored lubes, and it turns out that this was a candied lube blueberry, so the maltol should be present. On the negative side, we again see glycerol, but we also see furoic acid and citric acid, which actually is the base peak in the negative mode. And that again makes sense because we're dealing with a fruit flavored sample. So we chose to use chemometrics. And for those of you who aren't familiar with it, chemometrics is really a technique that analyzes instrumental data to identify trends in that data. And it reduces the subjectivity that happens when you're doing visual inspections between known and unknown, because it just looks for where are the maximum differences, right? So we use cluster analysis, principal component analysis, and linear discriminant analysis on this sample. So in cluster analysis, we associated with a heat map so that we could identify, you know, are these groups actually different, or could they really be similar? And they broke out into 12 different groups. We could clearly see our spermicides. This is an inoxidil 9 chain. These were all glycerol. No, sorry, these are glycerol. These were PDMS. So we could see the different groupings. Then we use principal component analysis. For those of you who've never heard of this, I like to kind of break it down like this, right? So the purpose of principal component analysis is to maximize the differences between the samples, and wherever they land, you can now say, oh, all of those things that group together mean that they have some similarities, right? So if we take this group of people, I'm sure you may or may not recognize them. I'm gonna ask the following questions, and then we'll, you know, orient them accordingly, right? So the first question is, how many of them have 2 legs? Well, they all have 2 legs, so it's not discriminating. How many have 2 arms? Again, they all have 2 arms. How many has 2 eyes? Again, they all have 2 eyes. How many have hair? And now we end up with 2 groups, those who have hair and those who don't. Next question, how many have real hair? And so we could say all of these people start to have real hair. You know, Oprah, you know, she's got money. I don't know if it's hers, but it looks good. So I'm gonna leave her on the neutral line. And then most likely, well, we definitely know he doesn't have his own hair, but most likely she may or may not, right? Now, how many have an identified gender, right? And with having an identified gender, it comes with certain biological pieces that we can use to orient our people. So the men kind of go a little south, the women kind of go a little north, and now we end up with 5 groups. So I can say any new sample that comes into this group has to be similar to an identified male with real hair who actually has his hair, right? So that is the purpose of principal component analysis. So when I applied it to my lubricant samples, I could see that, yeah, along these three principal components, I can start to see how these samples differentiate themselves. Now, so the blue and the brown kind of look like they are on the same scale in this 3D model, but if I incorporate other principal components that have unique features, these two groups will eventually separate. So if we look at what are the main components that differentiate these 12 groups, we start to see things like group 1 and group 2 are similar because they both have glycerol, but group 2 has lidocaine, which differentiates it. We also have our spermicidal group, which was really unique. Group 8 and 9 are both condoms because they have octylamine, but one has triglycerides and one has a methylphenyl glycidate. So then we used LDA, which is a way to determine if our model that we developed accurately classifies potentially new samples. And we used an external test validation set where we got brand new samples, plugged it into the model, and are we getting accurate classifications based on what we know they should classify as? And in this case, we got a 98.6% accurate classification. There were two samples that were misclassified. They were actually in group 7, but it was predicted to be in group 12. And I believe those were another set of condoms. And it was just the ratio, the proportion of components to each other that made it appear to be in group 12, but still really good accuracy. So real quick, because I know I got about 2 or 3 minutes. The good thing about the thing that you have to consider about chemometric analysis is that it does its best to differentiate based on the data that it's given, right? So if I look at all lubricants, water, silicone, oil, yes, they will start to separate out, but it'll start to separate out as oils, silicones, and waters. But if I want to get better discrimination with just silicone base, so like I know it's a silicone base, I screen for it, how well can I accurately classify an unknown silicone base? So these are different types of silicones. They all have their own Gaussian distribution on DART, as highlighted by the different colors, right? So the purple one on the negative side are your hydroxy PDMS, which generally show up on the negative side. Cyclics are in your blacks, et cetera, et cetera. So we ran about 60 silicone lubricants, and even though they are all silicone based, you can actually see there are differences between the PDMS ranges and the PDMS types, that we could get 11 different classes of silicone based lubricants. We ran PDMS on it, and we could tell that they are in fact truly different. So we tested the model using an internal test set, and we got a 98% correct classification. We tested an external sample set, and we got a 92% classification, which is still really good. It probably just means that there's 1 or 2 samples that wasn't classified in the model. And then I gave my students 3 blind samples. They had no idea what it was. They were able to classify 2 samples correctly. And the third one, they were like, I don't really know what it is, Dr. B. And I was like, perfect, because that's actually a water sample. So we were able to discriminate out even like, no, this isn't even supposed to be classified based on this model. And because IR is such another key instrument in forensic analysis, we compared IR PC as these same samples to DART. And while we got about 4 groups for IR analysis, we were able to elucidate and discriminate into 8 groups using DART analysis, which was a plus. Then we did water-based lubricants. We used the same model, but we added more flavored anesthetic sensations, and we were able to see 6 major classes. They were all easily discriminated. And then I said to myself, well, you know, whenever you analyze these things, I can smell the cherry, I can smell the apple. And we're analyzing all samples at 350 degrees C. And I said, man, that must be blowing these fragrances out of existence. Like, I'm not analyzing it because they vaporize too quickly. So we lowered the temperature to what we call cool dart, about 150 degrees C. And we can see that the profile at 350, which is primarily the lubricant-based glycerol, the dimer, maltol, et cetera, we now have more information about the fragrance that makes up the wet cherry fragrance. So we use Pearson correlation coefficient. I'm sure most of you have seen this, but if you haven't, it's basically an objective way to measure linearity between two samples based on the height of that peak. But you have to make sure that the same peaks are aligned, right? So if we have two samples of this Astroglide, you can see we have a pretty good R-squared value. But if we compare Astroglide with Wicked Jelly, where they have several peaks that are just not shared, not common, the R-squared goes down to basically 0. So we did that between all of the samples collected at Cool Dart and all of the samples collected at Hot Dart. And we could tell, like, yeah, there were some things that are different here. These all appear to be the same regardless. But the flavored lubricants are the ones that really kind of popped out. At Hot Dart, they all basically look the same because it's the same company, it's just a different fragrance profile. But when we dropped the temperature, we actually now can differentiate even between flavored lubricants because the correlation value is still high within the sample, but it was really low between samples. So we ran an LDA on that and were able to get 99% correct classification at Hot Dart because you're just primarily looking at the lubricant base. But if we use the same classes at the Low Dart, the accuracy drops a little, and that's because it really does require more classes because of that fragrance information. I'm going to skip over glitter shimmer, but the highlight of that is that we're looking at glitter shimmer particles that can transfer during sexual assaults or other close personal attacks. And we've developed a classification scheme and a characterization methodology that crime labs can implement when analyzing unknown glitter shimmer particles. So with that, I'd like to just say I'm really grateful that, let me rephrase and start like this. I put my whole tenure process on lubricants and condoms. I never had any idea that it would actually work, right? But in my heart, I was like, it's just a chemical mixture. It has to work. And by God's grace, it did. And we were able to identify major lubricant types. We were able to identify subcategories based on sensations, anesthetic, flavors, and even oligomeric ranges. We've also explored degradation markers, like how these lubricants degrade, which is something we're working on now, both external and post-coitus degradation. But ultimately, this all lays the foundation for characterizing lubricant samples, especially unknown. And I'm hoping to develop a better way of doing direct comparison between known and unknown lubricants, except just saying they both have PDMS, they both have octylamine, and they both have cornstarch. So I always live by this motto that Dr. King said: the ultimate measure of a man is not where he stands in moments of comfort and convenience, but where he stands in times of challenge and controversy. And this is where the forensic scientist must live, because we cannot be concerned with the story of the suspect, we cannot be concerned with the story of the victim, because our job is to always testify on behalf of the evidence. We understand what it means, we can interpret it, and we have to only speak to that regardless of what somebody wants us to say in order to achieve a conviction or to achieve a non-conviction. So with that, I'd like to, acknowledge National Institute of Justice, which has supported a lot of this research when nobody ever thought that we would get lubricant analysis funding. I'd like to acknowledge the research and mentoring program and the academic advancement programs at UCF, which has provided me some really great students, undergraduate and graduate alike. And here is the logo that my students have developed with guns, condoms, and drugs, because that is the work that we do. According to them, it is a, what do you call it? A rock, it's basically a rock and roll song, all in one group, sex, guns, and drugs. So with that, I will take any questions that you might have.
Thank you so much, Dr. Bridge, for your amazing